All right, so in this video, we're going to talk about atomic spectroscopy and moment of inertia. Okay, so discussing the moment of inertia is going to lead into rotational spectroscopy here. So for atomic spectra, right, we're considering here an atom absorbing or emitting light, right? That is going to cause an electronic or change in electronic energy level, right? And so, right, through that absorption event, right, we know energy has to be conserved. So we know if energy is conserved, that means, right, the change in the energy level, right, of your atom, which is going to be related to your principal quantum number n here, right, is related to the energy of that photon, right, which is related to h nu, right. So that, right, has to deal with the conservation of energy, right? That the change in energy in your molecule has to do with the energy of your light that has disappeared or appeared through emission or absorption, right? The other thing that must be conserved is angular momentum, okay? Photons, like electrons, have an inherent angular momentum. Photons' inherent angular momentum is 1 h bar, okay? Electrons is 1/2 h bar, okay? And so, again, we must conserve total energy as well as total momentum and angular momentum, right? And so that means if we want to conserve angular momentum, right, if we're losing or creating 1 h bar worth of angular momentum in light, okay, in photons, right, photon is light, okay, if we're creating or destroying that amount of angular momentum, that's got to go into our molecule. And so for that to occur, right, for me to create 1 angular momentum or lose 1 angular momentum, that's going to correspond to my angular momentum quantum number L increasing or decreasing by 1. Okay, so in order to conserve angular momentum, right, so this selection rule is due to the conservation of angular momentum. Okay, right? And so that's sort of the selection rule for atomic spectra, is that your angular momentum has to increase or decrease by 1, right? Right, so if you absorb light, that means your angular momentum has to increase by 1, right? Because you've taken this particle that has 1 h bar angular momentum, I need to absorb that, so I need to increase my angular momentum by 1, right? If I emit light, then that means the angular momentum has to decrease by 1 because now I've created a particle with 1 angular momentum, right? And so, right, so I can go from, say, L through absorption, I can go L equals 0 to, say, L equals 1, which is an S to a P orbital, right? Transition, okay? Right, but I can't, for example, do something like S to D, because that is a change in angular momentum of 2, right? It's going from 0 to 2, right, for L, and that is not allowed, okay? That has no allowable transitions, and so that will not occur whatsoever, okay? All right. And so now, right, we'll move on talking about moments of inertia, okay? Right, so for atomic spectroscopy, it's fairly simple. Just the angular momentum of your orbital has to increase or decrease by 1, depending on if you're absorbing or emitting light. Okay. So now we'll talk about moments of inertia and rotational spectroscopy. Okay. So when we talked about rotations before, right, we talked about rigid rotors, and typically we thought of as sort of like a linear molecule that is, diatomic, that's just rotating in space freely in 3 dimensions here, right? But when we talk about rotational spectroscopy, we're going to talk about all sorts of different types of molecules that have all sorts of different types of shapes, and they will have all sorts of different types of moment of inertia, right? Which the moment of inertia can be calculated for your molecule given this formula here, right? M is the mass of the atom, R is the distance of the atom from the nucleus or from the origin, right? And so I here is this moment of inertia given by this, okay? So each And this moment of inertia, right, is going to differ from molecule to molecule, and each molecule is going to have what are called 3 principal axes of rotation. Okay, and these principal axes are all going to be perpendicular to each other. Okay, and what makes something a principal axis of rotation is if you rotate around that principal axis, you are not inducing any type of rotation around any other type of axis. Okay, right? If I rotate this pen like this, right, you can't necessarily see, but I'm rotating my pen around one of its principal axes, right? It's not inducing a rotation around any other axis, right? If I rotate my pen, right, around an axis like this, it is slowly rotating around this axis, right? But if I cause rotation in my pen like this, right, this rotation is not rotating around any particular principal axis, and it's causing a rotation in this direction as well as a rotation in this direction at the same time. Okay, and so these principal axes of rotation are orthogonal to each other. There's always 3 per molecule. Okay, and each principal axis of rotation will have its own moment of inertia. Okay, so we're just going to label the axes of rotation A, B, and C, and thus, right, so if we label them A, B, and C, we'll label the moments of inertia as IA, IB, and IC. Okay, so that is what we're going to be using for our moments of inertia, okay, around our different principal axes. Okay. So there's different types of molecules that we can talk about, different types of rigid rotors. Okay, so we're going to focus on rigid rotors, meaning that they will not distort under any type of stress of rotation. Okay, this is an approximation. Obviously, when something rotates faster and faster, let's say even a diatomic molecule, so I rotate it faster and faster around this axis, right? That rotation eventually is going to cause that bond to lengthen, which is going to change its moment of inertia, which is then going to change the energy level separations and all sorts of things. So it has these kind of higher order effects. Okay, we will not focus on that here, but that can occur, and in future slides we'll kind of discuss that interaction between vibrational and rotational effects in these higher order type spectra. Okay. So we're going to assume rigid rotors, and for these rigid rotors, there's going to be 4 types that we will potentially talk about. There's spherical rotors. Okay. Spherical rotors mean that all 3 moments of inertia are equal. Okay. Symmetric rotors have 2 moments of inertia that are equal and 1 moment of inertia that is not equal to the others, but is not 0. Okay. Linear rotors have 2 moments of inertia that are equal to each other, just like symmetric, but that 3rd moment of inertia is exactly 0. Okay. And then the final are asymmetric rotors, which just have no moments of inertia equal to each other, and none of those moments of inertia equals 0 either. Okay. And there's a number of examples here on the slide detailing those types of rotors. Okay. And it has to do with the symmetry of the molecules, right? So spherical rotors are spherically symmetric. Okay. CH4, SiH4, SF6, these are all spherically symmetric molecules, right? Symmetric rotors have sometimes symmetry. NH3, right, has symmetry around 2 axes and not a 3rd, right? Linear rotors are just linear molecules, right? CO2, HCl, C2H2, right? Those are all linear. And then asymmetric rotors just are molecules with very low symmetry, okay? Things like water, and so on and so forth. All right. So pictures of these types of rotors, right, are given here, right? Your molecules, right? This is like water, right? In your asymmetric rotor, you have your symmetric rotor, right? And you can see these spherically symmetric and linear, right? So you can kind of see the pictures of these molecules, right? And kind of hopefully get a little bit of an understanding of being able to identify what molecule is spherically symmetric, just symmetric, linear, or asymmetric.